Hi there, I hope you're well. So we continue with Lecture E, Part 3. Um, Here is a quick summary of the results that I used. There are obviously lots of results, but here are some of the ones I'd like to highlight, especially for the test this coming Friday. So we showed you how for a single variable, uh, random variable, how to go from PDF to CDF, CDF to PDF, given the CDF of x and y as a function of x, how to derive the PDF of y, given the PDF of x and y in terms of x, to find the PDF of y, and then the multivariate analogs of these results you see up here. You should definitely practice these. Now we go on to functions of random variables. So remember that you imagine a stochastic scenario or non-deterministic scenario or probabilistic scenario in your head. It could be anything: coin tosses, stock prices, um, people crossing roads, phone calls coming into a call center, whatever fancies your tickles your imagination. Once you give a sample space, every point in the sample space is given a number on the real line. So, for example, up price movements could be assigned a numerical value, which allows you to do math. So you have a sample space, literally outcomes. Then there's a mapping from the sample space to the real line. And now from the real line, there are now functions on the real line. So for example, x squared or something. So now what we now have is a brand new function of random variables. So we saw something in the previous lecture. For example, how to find out the PDF of x squared. X squared was a function of the random variable x. But these are now a little bit more um, high level functions. The expectation of a single random variable x, which you'll notice I'm emphasizing that I'm in this upper part here going to calculate by using the marginal PDF or distribution of x, is as follows. The expectation of something random variable, is equal to, if you're working with a discrete random variable, notice what I say. If you're finding the expectation of x, take each possible value of x, multiply by the probability, sum it all up. Take each value of x, multiply with the density, quote unquote sum it all up or integrate this. The expectation, as you can see, is the probability counterpart of the sample mean in stats. The sample mean in stats says you don't have continuous variables in stats, you only have discrete by definition because they're observations. In stats, what you would do is you would take all the x values, add them up, and divide by n. But if you think about this carefully and you compare this expression, here's an x in the world of probability, here's an x in the world of stats. In the world of probability, there's a probability of x. In the world of stats, this is 1 over n. But if you think about this, if you have a sample, a statistical sample, what's the probability of having any one of those observations? 1 over n. So this is in fact saying x multiplied by probability of x, add it all up. In stats, we call the sample means. In the world of probabilities, we call them expected values. And we'll of course go a bit deeper into why we use words expected values. I could also have calculated just the expected value of x. Please notice up here, just the expected value of x. Down here, again, just the expected value of x. But I can also calculate the expected value of x by using the joint PDFs. So again, what I would do is, quote unquote, the intuition is take each value of x, multiply with the probabilities. Because you're now working with joint distributions, it's the joint probability. So you'll have to do this sum twice to get this expected value. You'll have to do this in the integral twice to get the expected value. Let's do an example. You remember your stock prices going up and down example. So equal probability going up and down, right? There's no price staying constant. And now you remember that you had 8 possible outcomes in the sample space. We then define two random variables called baby u, baby r. Baby u is right here, total number of up price movements, and baby r was the length of the longest successive run of either up or down price movements. In the last lecture, we derived the joint PMF or joint probability distribution. So you can see that there's no mass here. There's in fact no probability that u will be 0 or will be equal to 1. No probability here. So you only have pillars of height 1/8 here, height 1/8, 2/8, 1/8, and so forth. This is the joint distribution. And you remember that what we did last time was, if you just want the probability distribution of u's, then you would take the joint distribution for this particular value of u0, you would add up all the probabilities across all possible values of r to get 1/8. That's exactly what this sum means. Again, for value of u is equal to 1, add up all the joint probabilities for all possible values of r, get 3/8. So these numbers, red numbers, are the probabilities of observing the u's only, and these purple numbers are the probabilities of observing the r's. And again, how do we get 2/8? With the value of R1, I would sum up across the joint probabilities for all possible values of U to get 2/8. Now what I want to do is I want to find out the expected value of U and the expected value of R. So before we go on, basically what you're asking is, U was the total number of times the price went up. So you're asking, if you were to follow a stock for 3 days, what's the how many times can you expect the stock to go up? Quote unquote, in the world of stats, it would be on average, how many times does the price go up over 3-day periods? Here's how we do it. If you want to do it by the marginal distribution, if you remember, I began this thing by the marginals, right? So I'm doing this first. What you would do is, literally by using the marginal distribution of baby u, to find the expected value of u, the expected number of up price movements for 3 periods, I would take each possible value of u, so that means the price never went up, u0, the price went up in 1 period, went up in 2 periods, went up in 3 periods. Take all those values of u, 0, 1, 2, 3, multiply with the corresponding probabilities, 1/8, 3/8, 3/8, 1/8. So I've done them for you. You really should sit down and go over this before Friday, because that's not something you should do in real time, right? Leave the gangsterism for gangsters. So each possible value of u times the probabilities, sum it all up, and the answer is 12/8. What this means in plain English is, if this was a bar, not an alcohol bar, but a metal bar, or like some sort of a wooden plank, where would you have to put the fulcrum for this plank or this bar to balance? If you put it over here, the bar would tip over because most of the weight is on the right. So you would have to put it exactly here for the thing to be exactly balanced. The weight on the left is equal weight on the right. In a finance example, 12/8. Sorry, I suck at arithmetic. True story, I was kicked out of elementary school. It's a long story as to why. And I kind of missed all the arithmetic they drilled into you. So math, I'm okay. Arithmetic, I'm terrible. So 12/8 would be, let's see, 3/2-ish, 1.5, right? So that means what? If somebody were to follow the stock over 3 days, the you would expect the stock to go up 1.5 periods on average. And by the same logic, I can now compute the expected value of R, the length of the longest successive run. R1 means that you should think in your head what this means. It cannot be UUU, cannot be DDD, cannot be UUD, cannot be DDU. It has to be UDU, DUD, right? Length successive run is exactly 1. R2 would be, of course, UUD, DUU, right? And R3, of course, would then be UUU or DDD. So to find the expected uh, length of the longest successive run, take each value of R, 1, 2, 3, 1, 2, 3, multiply corresponding probabilities, and you get 2. So if I observe a stock over 3 periods, I would expect the length of the longest successive run to be 2. So I wouldn't, right? That's the expectation, right? So you would observe things like UUD, DUU, right, and so forth. All right. But can I get the same answer by the joint distribution? You should spend some time thinking about this. How in God's name did we arrive at these from the joint distribution? And now what you're asking is, can I once again calculate the expected number of times periods that the stock price is going to go up, but this time using the joint distribution? And by now, I hope you appreciate how these things work. The way these things work is, if someone asks you to find the expected value of something, the rule is, in a discrete world, essentially you're looking for that animal in here, which is u, and you're multiplying by a probability, right? What that probability is depends on whether you're working with marginals or with joints. So now you're working with joints. So now what you have to do is take each value of u, 0, 1, 2, 3, and multiply by the corresponding joint probability. So 0 times 1/8, 1 times 1/8, 1 times 2/8, 2 times 1/8, 2 times 2/8, 3 times 1/8, and if you get the answer, you get the exact same value that you got by using the marginal density or the distribution. As an exercise, you should verify that if you use the joint probabilities, you should get the exact same answer on the previous slide for the expectation of R. I know this is confusing, but bear with me for 1 second. I should have done this last lecture. You remember that we imagined a joint distribution between x and y. You can see on the z-axis is the density. Here's the gray area to support the density. X takes some values between 0 and 1. Y takes some values between 0 and x, right? Hence this lower shaded triangle. If somebody had asked you to just the distribution of x, so you can see x goes from 0, 0, 1, 1. You would actually have to imagine collapsing. So imagine stepping on this gray triangle. So things collapses onto the x-axis. And you can see by looking at it, if you were to step, which I'm not going to draw in my slides because we'll never finish, if I were to thump this thing, this wedge, if I was put my foot on it, then what is going to happen is going to get crushed, but most of the mass is going to be like this. So no wonder when you find out the quote-unquote density of x, the density is higher over here because there's more mass over here and less mass over there. How did you do this? What you did was you took the joint densities, right? So imagine picking a certain value of x. How would I get this area compressed, collapsed, and get that value right there? You would integrate, you would take all the joint densities for all these possible values of y, quote unquote, sum them up or integrate them, and that's how you got this. That's exactly why you see here. Density of x is gotten by integrating with respect to y on the joint densities. This is the expression. Now, excuse me, how do I get the expected value of x? So once again, we should remember the rules. The rules are to find the expected value of x. I should have done this. Sorry, guys. Maybe I'll help you a little bit. The expected value of x, this thing, if you wrote it in general form, would have been x into f of x times dx. I don't know who has worse handwriting, me or Tommaso, but I think definitely me right now. And then you would so x, the density of x, you can see that's 3x squared right there, dx, and now integrate across all possible values of x, which are from 0 to 1, and the answer is 3/4. So that means now, if you were to balance this bar somewhere, the fulcrum would have to be at 0.75 for it to be equally balanced. Why is this drawn this way? Because what about the density of y? Y takes values from 0 to 1, 0 to 1. And if I want to get the density of y, I would imagine summing up across all these joint densities with respect to all the possible values of x. So if I sum this way, right, for this value of y, I'm summing up this way to get this thing right here. You can see most of the mass is this way, looking at the y-axis perspective. So no wonder the density is high like this. So you've got to twist your neck to see that this is the y-axis. That's the density of y. And the expectation of y. Where would I have to put my fulcrum for this bar to balance? The value of y times the density of y, dy, integrate respect to y, and the answer is 3/8. Could I have gotten these answers for expectation of x, expectation of y from using joint PDF? Of course, because the rule was I have to remember if I want the expectation of x, take x, and now since I'm working with joints, multiply the joint density. And now I have to integrate twice with respect to x and y. Well, here's your x, right? Here is your density of x. Here is your x. There's your x. Where is your density of x and y? That's of course given to you by right there, density of x and y, which is 3x. So that's of course, I should have not put this x over here because I'm very sorry. It should be 3x. But of course, x times 3x then becomes squared. I'll fix it on the slides that I post eventually. And the answer is going to be 3/4. In the same way, this is a typo because you can see I want the expectation of y. So I would want y, but I want here's your y, here's your y. But now I want the joint density of x and y, which of course is 3x. So this should have been simply 3x. So what I want is the integral of y, 3x times dy dx with respect to x and y. Those are the ranges. And the answer is 3x, exactly as what you got by using the marginal densities. So it, again, the expected values are quote unquote, where would you have to put the fulcrum for it to balance the power? And I'll give a more quote unquote econometrics interpretation very soon of what it means to say expected value. So let's now go a little deeper. Um, what about an expectation of something grander? Right now, you did expectation of x, expectation of y, expectation of r, expectation of u. But what if you gave me a function of x, expectation of x squared? What if you gave me a function of two random variables, expectation of x squared plus y cubed? So as long as you keep a cool head, we're golden. Because why? If you want the expectation of gx and you want to use marginal densities, take the gx, now multiply with the probabilities and sum them all up. Not that hard. Take the gx, multiply by density, integrate. If you want the expectation of something that depends on x and y, put that something that depends on x and y over here, multiply the joint probabilities, sum of them twice with respect to x and y. You want the expectation of something that depends on x and y, put that creature over here, multiply the joint density, and now you have to integrate with respect to x and y. Not that hard. Let's go back and do an example. Your good old up and down stock price movements. We know how to do expectation of U, up price movements. We know how to do expectation of R, length of longest successive run. Now let's do something more complicated. Let's find out the expectation of U plus R. So now what we're looking for is, if you want to look at the slide, we're looking for, I have a function of two random variables, and I'm asked to find the expectation. So we're not working the top thingy, we're working down thingy. But even though it's a expectation of two random variables, I will use this method. I'll also show you how to use that method. Stay tuned. So coming back, U R, and I want to find the expected value of U plus R. One way to do this is by the joint PMF, because let's take all the possible values of U plus R. So I want U plus R times the probabilities. So what are the values? I'm only going to read off the values with this mass. U plus R is 0 plus 3, 0 plus 3 times 1/8, 1/8. U1, R1, the sum is 1 plus 1 times 1/8. 1U, R2, right here, times the probability, 2/8. 2, 1 is the sum, times probabilities, 1/8. 2, 2 is the sum, times probability, 2/8. 3, 3 is a sum, and then the probability, 1/8. The answer comes out to 7 divided by 2. But could I have done by a marginal PMF? Well, how could that be? It's actually very simple. Look at all the possible values of U plus R. There's 3, there's 2, there's 3, there's 3, there's 4, and there's 6. So you can see 2 only shows up once and happens to probably 1/8. So 2 with 1/8 probability right here. But notice how 3 happens with 1 time here, probably 1/8. probably 2 eighths, probably 1/8. So 2 plus 1 is 4/8. So you can see that u plus r is equal to 3. That happens probably 4/8. So by this token, I've defined a brand new variable called z, which is equal to u plus r. All I have to do is find out all the possible values of u plus r. Those are listed right here, and their probabilities. And then we're good to go, because if you want the expectation of u plus r, you actually want the expectation of z, which is of course the values of z, 2, 3, 4, 6, 2, 3, 4, 6, multiply the corresponding probabilities. That's exactly what you see here. Add them all up, and voila, you get the exact same answer as you got by the joint PDF. See, so there are tricks to doing this. While you're on this subject, would you expect the expectation of the sum u plus r to be the same as the expectation of the sum r plus u? I'll give you a few seconds to think about this. I wish we had eye clickers. Actually, no, I don't. So what's the answer? The answer is they should be the same. Why? Because the way you found this thing was by adding these up and imagining a sum z. The sum z doesn't matter. It doesn't matter whether you define it as u plus r or r plus u. So these two expressions are going to be exactly the same. So what you saw by example right now is I gave you a function of two random variables, r and u, and I want you to find the expectation. For many of you, this approach looks easier than that approach. Look at this, messy, long, you can make mistakes, and so forth. So it appears for the time being that the marginal PDF approach or marginal density approach is faster, leaner, cooler than the joint PDF approach. And so many of you, when are asked down in future advanced courses to find the expectation of two random variables, something that involves two random variables, you try to find the PDF of that function called z and then use this approach. And many of you will want to avoid this approach. But as you're about to see, sometimes this is faster, better than doing the marginal PDF. What kind of witchcraft is this? Here's a nice devious example. You remember your good friend? Somebody asks you for this particular joint distribution to calculate the expected value of a function of xy. Which function? You ask expectation of x. Well, expectation of x plus y. Here's one way of doing it. If you want to use a marginal PDF approach, just like you did over here, this kind of approach, right, marginal PDF approach, you could do the following. You would have to define z1 to be equal to x plus 1 or y. And then you would have to derive the density of z1. But if you remember, well, if you had the density of z1, we're cool. Because all you would do is you would take the total value of z1, multiply by this density which you think you know, and we'll be all right. But this is the exact same problem I gave you in the last lecture. And let me sort of jolt your memory as to how, quote unquote, hard it was to get the density of x plus y. Let me jump to the next slide. Do you remember how we started at the end of last lecture? We had this picture, and we were asked to find the density of x plus y, right? So we use the Jacobian method. To use the Jacobian method, I need to express the x in terms of z's. Since I only have one z1 right now, you remember the trick was if you're already given one z1 to begin with and nothing else, you should try to define a second z2. So z2 is equal to y, z1 was x plus y to begin with, and now what I'm going to do is I'm going to rearrange these to express the x's in terms of z's, y's in terms of z's. And then by the Jacobian method approach, I would have done exactly what you see over here, right? So I believe what I did was I stopped here last time. I showed you this density. And then where we stopped was to show, well, Jesus, well, if you want to verify this is actually a legit density, you would have to verify that the total area under this curve is equal to 1. To do that, you would have to find the quote-unquote region in which thing is supported. So I'm not even going to try and color this, but maybe I'll try a little bit, right? But this region was this triangle thingy wingy wingy is the support of density z1, z2. So what you'd have to do is you would have to integrate to see if this is in fact a right answer. You would have to integrate this joint density over that area and hope that the answer was 1. This is a really long exercise. Like, I mean, this is going to take you some time. Trust me. One wonders if you can do it the other way around, which was the joint PDF. Of course you can. You want the expectation of a function of x and y, precisely x plus y. So all you have to do is keep a cool head, write down the function, multiply by joint densities, and now take integrals twice. And voila, we're done. X plus y, x plus y. This, of course, is the joint density of x and y. Remember that we said right here, the joint density of x and y is 3x because I get that answer from right over there. And you can see in less than 5 minutes, you'll have your answer nice and clean. No need to do this horrible, ugly math that we did last time. So anyway, pain is good, pain is gain. So you should, to test your principles and understanding, you should do this anyway. I never end up deriving f of z1. You should derive f of z1 on your own and verify that you get the same answer for the expectation as the joint, using the joint PDF approach. Let's do another example. Again, you have a different joint distribution. This one is now supported on a square. I think I remember saying that that you can kind of suspect that x and y are maybe independent, right? Because you can see that any conditional density would always look the same, no matter which value y you used or which value x you used. Now you want to find out the expectation of, again, a function of x and y, x plus y. Same trick, x plus y. And now you have the density over here, which is the joint density of 6x squared y, 6x squared y right here. Now you integrate twice over this entire expression, and the answer is 17 over 12. Okay? And of course, if you could have done it a different way. You could have found out just a separate density of x plus y and gotten it from the marginal PDF. You probably should do that. Now we go to more advanced functions of random variables. So now you have an expectation of a function of x, 1x. This function of x says, give me x, subtract the expected value, raise to the power n, and then take expectations, which has a very fancy symbol, sigma to the power n x. It's not very intuitive. So when we look at instead of looking at the nth central moment, let's look at the second central moment. So replace all the n's by the number 2, and now all of a sudden things look familiar. You want the expectation of what creature? The square of x minus expectation, which is sigma squared x. If you look carefully, that says sum. You're trying to find the expectation of x minus ex squared. That's x minus ex squared. Since you work in discrete, you will multiply with the marginal, the probability of just the x's. If you're working with continuous, it will be the density. And now compare this expression with this expression. This is in fact your variance that you saw in stats, right? Because in variance, you took each value of x, subtracted off the mean, squared it, divided by n, and summed it all up. That's exactly what you're doing. X, x. Your mean now gets replaced by expected value, square, square, and instead of 1 over n, which is in the stats, just the sample, now use the actual probability. I'm now going to compute the variance of x directly from the PDF of x. Okay? Let's do, excuse me, a simple example. You remember the u's and the r's. So I know that if I want to find out the variance of u's, I have to take each value of u, subtract the mean of the expected value, square it, multiply by probability. So before you can do this, you have to first find out the expected value, which was done previously as 12 divided by 8. Now let's go a bit slowly. How do you read this expression? Take each value of u, subtract off the expected value. So 0 minus 12 over 8 squared times the probability 1 over 8. Next up, 1 minus 12 over 8 squared times its probability 3 eighths. 2 minus 12 over 8 squared times that probability 3 eighths. 3 minus 12 over 8 squared times its probability 1/8. Do this, the answer comes out 3/4. And so You remember that the variance gives you a sense of dispersion. So you can balance a bar, the expected number of up price movements over 3 weeks is 1.5, and with the variance of 0.75. So right now, you can think of variance as a sense of dispersion. Why? Because if you have values of u that are far away from the expected value, when you square them, that number gets amplified. So the variance tends to be bigger and bigger and bigger if you start to stretch this distribution out, right? So if this pillar moved over to the left, that pillar moved over to the right, the variance would go up, even though the mean stays exactly the same. So in the same way you get this point, I think you first find out the expected values, already done for you. I don't know why didn't show the calculation here, but anyway. And now, of course, same thing here. Take each value of r, subtract the expected value, 1 minus 2 squared times the probability. 2 minus 2 squared times its probability. 3 minus 2 squared times its probability. And becomes half. You might be tempted to say the graph on the right has less dispersion than the graph on the left, but you remember the graph on the right is for 1, 2, 3, whereas the graph on the left is for 0, 1, 2, 3. So there are more possibilities out there. Let's do it now for densities. Here's your joint PDF of x and y. You know how to extract just the density of x, just the density of y. You already know how to find out the expected value of x. And now if somebody says given the variance of x, you use this formula. So here's, you want to take the integral of x minus expectation squared. Expectations are 3 over 4. So what you want to do is take the integral of x minus the expected value of x, 3/4, square it, multiply by the density of x. The density of x is 3x squared, 3x squared. And now to remember that x is between 0 and 1, carry the integration, there's your variance right there. Same thing with y. What you want is y minus the expected value, which is previously calculated as 3 over 8. So y minus 3/8 squared times the density of y, which of course is 3 over 2, 1 minus y squared. When you do the whole integral, you'll get an answer. Of course, you should do this and work it out on your own. Now let's go to conditional expectations. So conditional expectations, so let's go back a little bit. You get the sense that the expected value of u is the center of quote-unquote center distribution. What sense? Equal mass to the left, equal mass to the right. Same thing over here. So expected value of x would be, I would have to put the needle at, if I put the needle at 3/4, which is roughly around here, then the mass on the left would balance with the mass on the right. Right here, it would be, I would have to put at 3/8 for to the left for this distribution to be balanced on the fulcrum. So it's the quote unquote center of distribution. Please don't take the word center literally, but you get the point that I'm trying to make. As long as you understood that, the expected value of x given an event is exactly the same thing. It's center of some distribution. But this time, the distribution happens to be affected by some event A. So if you know that an event A has taken place, and you want to find out the expected values of x's, what you would do is you would take each value of x, but this time you will multiply not by the probabilities, but by the conditional probabilities. If you know that some event A has taken place, you will multiply not by the density of x, but by the conditional density of x given the event A. So I'm going to compute this animal directly from the conditional PDFs of x given A, or PMF of x given A. Bear with me. I know this looks very scary. It's actually on purpose, but let's start slowly. From the joint density on the left, you were able to pull out just the marginal density of x, and you already know the expected value of x is 3/4. You were also able to pull out the density of y, and I'm not reporting the expected value here because it won't matter in a few seconds, but what I want to do is I want to come over here. Somebody says, give me the expected value of x given y. Again, this is really, 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 really important. So I'll play with pictures over here. What that means in plain English is x and y have a joint distribution. So when you observe an outcome, it must come with an x value and it comes to the y value. I sent someone out to observe an outcome from this distribution. They report to me the value of y, but not the value of x. So they tell me they've observed a dot, and whatever dot they observed had a value of y somewhere over here. Well, if that's the value y they did, then the values of x's must be have to be between here and here. So if they saw that value of y, the corresponding values of x's, the condition will be between this value of y and all the way to 1. And now, just like any other distribution before, I could collapse this density, just this part, onto itself, right? Just this part to the right of y and to the left of y. And when I put it on the x-axis, I might get a distribution. I'm just making some shapes up. For a different value of y, this would be the support, and I might get a completely different shape. So these would be your distributions of x given y. The distribution of x given a certain value of y. So imagine, and I did this on purpose, imagine that someone tells you that they saw an outcome x and y, but the value of y was half. So whatever the value of x is, it has to lie somewhere in here, right? Somewhere on that line. And it has, if I were to collapse its density, it would actually have some shape. So right now the shape that you see up here is not to be taken literally, I'm just imagining it. And that distribution is going to have a center. And that center will be the expected value of x given that particular value y. So remember that this expression thing you are here, this is the density of x values given that y is equal to half. And then it has a center of the distribution, which is your expected value of x given y. How would I find this? For that, you come over here. So, expected value of x given y. Now, remember the rule was if you look back at the previous slide, take the x's, multiply the conditional probabilities. So, if I want the expected value of x given y, I take the value of x and then multiply by the conditional density of x given y. But you should know by now that the conditional density of x given y is the joint density of x and y divided by the density of y. So here's your x, here's your x. This expression is your conditional density of x given y. And how do I find this out? I found this out by taking the joint density of x and y and dividing it by the density of y. So what I did was I took 3x divided by 3 over 2, 1 minus y squared, and I would get 2x over 1 minus y squared. I then multiply this by x, and then integrate respect to x, but you have to remember the range of integration. Oh my god, range of integration is really important. Whatever value of x you take over here, the x's have to be between y and 1. Between y and 1. So here's a general expression for the expected value of x given any value of y, right? Give me any value of y, and I will tell you what the center of the distribution of x given y is going to be like. In this particular example, you wanted y to be equal to 1 half. So when I plug half in here, I get the answer is 0.77. So if I kept going down here, the actual density of this thing, I don't even know if this is actually correct, but I think it's correct. I actually typed this, using the value of y. I actually did this. So this is, I think, the density of x given y is equal to half. The center of the density is at, in fact, 0.77. And that's where the bar would be exactly balanced, right? Now, down here, I say, notice that y is useful information for finding the expected value of x. Why? Because if somebody went and picked an outcome from this distribution, and you asked me to guess the value of x, I would say the expected value of x is 3/4 on the basis of this information. But when you give me some information that you also saw a certain particular value of y, for example, y was equal to half, then the expected value of x now depends on the value of y. So I get a completely different expression. So now y is in fact useful because knowing y gives you a better way to forecast the value of x. Because if you did not tell me the value of y, I would just have to guess that x could be somewhere in here, and I take the quote-unquote center distribution. But if you give me a specific value of y, then that narrows down the ranges that values x can take. Now I know x can be somewhere here, and I take the center of that distribution, which now is given by this expression, which in this example was 0.77. All right, in the same way, let's find out the expected value of y given x. So I'll go a bit faster this time. Again, the intuition is again exactly the same. Someone is sent out, but this time they tell you the value of x. And now you know that whatever value of y is, it has to be between 0 and x. For any given value of x, if you were to collapse its density onto the y-axis, it would give you a density. I'm making a fake one right there. The center of the density would then be the expected value of y given x. That's exactly what you see here. So give me any arbitrary value of x. So let me switch to a highlighter. Give me a value of x. I know that y must be between 0 and x. It defines a PDF, the conditional PDF of y given x. The center of the distribution, and that center, of course, is the expected value of y given x. How would I find it? I would say take the value of y, not here, multiply the conditional density of y given x. And how would you find the conditional density of y given x? I've done it for you over here. You would take the joint density of x and y and divide by the density of x. Right? And then the answer is x over 2. Beautiful. And again, notice how knowing the value of x is in fact useful, because without the value of x, I would have said the expected value of y was always 3/8. Never mind what you saw. But once you tell me that you saw a particular value of x, I can sharpen my forecast of y. I can now say, aha, given what you said about x, I forecast that the value of y is going to be x over 2. Literally the center of this thing right here. Now we do variances of these conditional distributions. Just like if these distributions have, like any distribution, if you have a distribution and a center and a variance, that's a sense of dispersion, like variation data. Same thing with the conditional distributions. Nothing's different. Students get, when I first saw this in grad school, of course it was a fake grad school online. I think I paid like $3 plus HST. The first time I saw this, I'll be honest with you, I started to question why I'm doing grad school. At that point, the picture of my parents appeared, and the very disappointing faces that if I didn't go through grad school, I'd be disowned. So there goes my dream of driving cabs or growing tomatoes or being a DJ. So it freaked me out. I'll be very honest. And then it takes a little bit of time to see. Wait a second, it's not that scary because you're being asked to find out the expectation of something, this expression squared. And the difference now is that it's on a conditional event. So instead of using probabilities, you now use conditional probabilities. But then you remind yourself that x minus quote unquote center of the distribution squared is nothing, of course, but the variance. So this would give you the variance if the x's were discrete. This would give the variance if the x's were continuous. Let's do an example. Same thing I did before. You remember that I imagined that y was equal to a half. If it was, the values of x would have to go between half and 1. Behind the scenes, you can imagine a distribution which has a center called expectation of x given y. But this distribution surely has some variation, which I've now gone as a black arrow right here. To find that expression, I now go to the next slide. So why did I show you this slide? Because if you go back to find the expectations, to find the conditional variances, I have to first find out the conditional expectation. So I have to first find out the expected value of x given y before I can proceed. Here's a general formula. Here's the number for the specific value of y is equal to half. Once I have this, we're done. Because what's the conditional variance of x given y? Take the x's, here's the x, here's the x. Subtract off the expected value of x given y. I showed this to you in the previous slide, and I'll show you again. Here's the expected value of x given y. Here's the expected value of x equal to y. X minus center of the distribution squared multiplied by density. But density of what? Since you're trying to find out the variances of the x's, it has to be now the conditional density of x given y. So this expression right here should be the conditional distribution of x given y. And that's, you can see that's exactly what you see over here. Yeah, right there, right? This thing right here. So again, integrate, open bracket squared, x minus center of distribution, which is expected value of x given y, multiplied by the conditional distribution of x given y, f of x given y. Dx, integrate, and now of course you get crazy answers if you're not careful. You have to remember that once you give me a value of y, the values of x's must be between that value of y and all the way to 1, right? So that's why the integration starts at the lower bound of y and goes all the way to 1. Now we do some key theorems on expectations. Excuse me. X and y are jointly distributed random variables. A, B, C are numbers. Expectation of a sum or difference, the sum or difference of the expectations. I know I said that really fast, so I'll go a bit slowly. What you want to find out, say, is this expression looks like this expression. Expectations, not romantic ones, unfortunately, but mathematical ones, are like derivatives. They're sum, derivative of a sum is sum of derivatives. They're like integrals. Integral of a sum is sum of integrals. Right? So these are known as linear operators. So you want to show this result. What throws people off, and this is especially for MFEs, you're going to take Angelo Molino. And Angelo Molino studied at Harvard. And Harvard uses this sort of stuff. And because you're at Harvard, you don't need to tell students what the expectation is over. But, that's not really good because you're wasting time if you don't remind the audience what the expectation is over. Remember, I've spent some time showing you how expectations can be done about joint distributions or marginal distributions. So anytime you see such a creature in Angelo's course or anybody else's course, the first question you're asking is, with respect to what density am I doing this? And I'm telling you, you're doing this over the joint PDFs. Let's prove this. And I'll do a fast proof. You should, of course, do carefully on your own. You want to show what happens to this thing right here. By definition, you're trying to take the expectation of this creature right here, take the creature, multiply the joint density of x and y, dx, dy, integrate over x and y. Because integrals are linear operators, integrals of sums are sums of integrals. So I've break this up in 3 parts. The first part is right here. I pulled the a out already, so right here. Second part then be I put the b out already, but I've left the x part in there. The third part would then be I pulled the c out already, but left everything else in there. Now, I'm going to play some clever tricks. I'm going to leave this as it is. So this stays exactly as it is. Nothing has changed. Right? Here's your b, here's your b. But what I'm going to do is I'm going to take this x and I'm going to bring it outside. Because when I do this, what should this creature be? Take a good look at this one right here. This is integrate the joint density of x and y with respect to y. But that should give me the density of, that's right, you guessed it, x. So this term will become x. That term will become density of x. By the same token, if I pull y out here, what's this expression right here? This, of course, is nothing but the density. So integrate the joint density with respect to x. And that should give you, of course, the density of y. And here's your y here separately. So there's your y right there. And now take a look at the expression. If I do double integration over the joint densities, the answer, of course, should be 1 because you're summing over the entire density. So a times 1 is 1 plus b into this creature right here, which if you now look carefully, of course, was x times the density of x, integrate all values of x, is b into expectation of x. C into this creature, which is integral of y into density of y, integrate all values of y, but nothing but c expectation of y. So Very easy to prove. Not that bad, right? So let's put it in action. I sh- Earlier I showed this to you by doing double by computing this over the joint density. So this is what you're saying is I've shown you now the left side, right? But what the theorem says is you could do it over the joint density, or you could use the fact that the expectation of x must be expected equal to expectation of x, expectation of x plus y must be the expectation of x plus the expectation of y. But voila, earlier we showed the expectation of x was 3/4. Earlier we showed the expectation of y was 3/8. When you sum them up, you get the exact same answer that you would have gotten by the joint PDF method. Nice. Now this is where Molino gets really upset. Some people, get really inspired. Maybe they drank a bit too much tequila, and they say, well, if the expectation of x plus y is the expectation of x plus the expectation of y, some gangsters seem to think that the expectation of a product is the product of expectations. One more time. Expectation of products, some people mistakenly claim, is always equal to the product of expectations. That's not true. What is true is this expression. And once again, when I first saw this in high school, not high school, sorry, graduate school, actually I saw this 16,000 years after grad school, it scared the shit out of me, honestly. Because what in God's name does this even say? And that's because the fake prof I had at my fake university went to Harvard. Harvard shows that teaches their students this stupid ass rule right here, which unfortunately is so misleading, it's not even funny. Somebody has to tell you, like pompous Harvard asses, that this expectation is an expectation that behind the scenes they've done over the joint PDF. This expectation is done over, because you can see is expected value y given x, so it must have been done over a conditional PDF. In fact, you know the conditional PDF. It must have been the PDF of y given x. And the fact that you have a subscript here is to remind the Harvard students that this particular expectation is being done with respect to a marginal PDF, in fact, the PDF of x. So, what is always true is if somebody tells you, give me the expected value of x times y, it says in words, first find out the expected value of y given x. This is going to be, by the way, guys, this is where you really need to spend some time thinking about this, right? There's no sleep in grad school. If you're sleeping more than 4 hours, you're doing something wrong. I'm not sleeping more than 4 hours. Life sucks. This is not, if I had fed in a numerical value of x, this would be a number. But if I don't feed a numerical value of x, this would be a function of x. So find the function of x. Which function? The expected value y given x. Then multiply it by x. Then find the expected value of this creature, but this time use the PDF of x. And what you'll find out is that's exactly the same as finding out the PDF of x times y if had you used the joint PDF. All right, proof time. Let me pray right now. I want to find out the expectation of x and y, right? And I want to break it down on the right hand side. Let's find this creature on the left side by using joint PDF. So you got to keep a cool head here. So here is what you're trying to find the expectation of. Since this involves two random variables, you will now multiply by the joint density of x and y, integrate respect to x and y. But boys and girls, ladies and gentlemen, what's this? Right? This is in fact nothing but, you remember the conditional densities? The conditional density of y given x was a joint divided by x. But if I rearrange, the joint PDF of x and y is the PDF of y given x times the PDF of x. And now I'm going to use the same trick I did in the previous proof. I'm going to pull the x out over here. Because what that leaves me is, I hope I don't miss. That's what happens when you've done too much alcohol as an undergrad student. Take a look at this creature right here. Voila. Take time y times the density of y given x. integrate all over, and that of course must be nothing but the expected value of y given x. There's your little x right there, there's your little x right there. There's your density of x over there, there's your density of x there. So what you just said is take x times expected value y given x, and then find the expectation using the density of x. And that will be equal to the expectation of x and y had you done the expectation using the joint PDF. Pretty cool. Let's see how to use it. Uh, I have used this example, and I have in fact done it for you. I first do expectation x times y from the joint PDF without using the theorem that you saw over there. So here's your x times y. Here's your joint PDF of x and y. And then you should carry out the integral to see the answer is 3 divided by 10. But now let's see if we can do it this way. In a previous slide, we showed that the expectation of y given x was x over 2. That's this feature right here. Right? So here's your expectation of y given x, your x over 2. And now we know that we have to multiply this by x. Here's your x, here's your x. X squared divided by 2, right? That's exactly what you see here. And the subscript reminds us that you should now get the expectation of this creature, but use the density of x. So if I want the expectation of this creature, but I want to use the density of x, put the creature down. That's your x squared divided by 2. And now use the density of x. Integrate across all values of x, which of course are now between 0 and 1. And voila, but. Someday, one day, eventually, the answer comes out to be exactly as if we had done it by the joint PDF. This is an amazing result. Like, think about how much work you can save. Like, do you really want to do this nasty, horrible, crappy integral over here when you can actually have this much faster technique down there? Right? Let's now do something a little bit different. I just showed you that this is always true. So, but what about this thing right here? Well, let's see. Here's what you saw 2 seconds ago. Now imagine that x and y are independent. You really should sit down and say, how do I know something's independent? There are two ways. If the joint density of x and y is equal to the density of x times the density of y, that's one way of knowing if x and y are independent. Or if the density of y given x is the density of y, you know that y and x are independent. So therefore, take a look at this expression right here. So go back, so you know that this is in fact true. You just proved this. And now if I expand the integral out, take a look at this expression right here. That's exactly what you see over here, right? Now, your y times the conditional density of y given x, dy integrate. But if x and y are independent, the conditional density of y given x must be equal to the density of y. So this entire expression then becomes the expectation of y. And expectation of y is actually a number. It's not a function. You gotta know why. Why is this thing a function of x, but that thing in number, right? Think about this. And the reason is because expectation of y is just the central distribution of the y distribution, which is fixed. It never moves. But the expectation of y given x is center of which distribution? The distribution of y given x, which could move depending on the value of x. Draw some pictures and you'll see. But then we're done, because if you go back to this proof, you had an x over here. You used to have an expectation of y given x. Now you replace that with the expectation of y, which being a constant comes outside. And then what you of course left here is literally the integral of x times its own density, which of course is the expectation of x. So beautiful. Only if x and y are independent variables, only then does the expectation of x times y equal the expectation of x times the expectation of y. So if they are independent, this result holds true. But for the love of God, not necessarily the other way around. It could be a sheer coincidence that this could be true. despite the fact x and y are not random variables. Here's a common mistake some people make. They think that the expectation of a function is a function of the expectation. So for example, the expectation of 1 over x, or x inverse, is the inverse of the expectation. Not true, as you can see. Some people think the expectation of a ratio is the ratio of the expectations. By example, you can see, not true. So don't make the mistake. Do not piss off Angelo. Okay, so I know this is not true. I can't say that the expectation of a function is a function of the expectation. But can I say something about these two things, vis-a-vis each other? Actually, I can. You know that for a concave function, if it, what you said was, remember that lecture C something, I think. You said for a concave function, the function of a weighted average of x1 and x2 is always been equal to the weighted average of the function of x1, x2. But since alpha, you have to go back to slides. I never said alpha is in the closed interval, right? So what I said was it's in the open interval. So now these alphas can take on the interpretation of probabilities. So probability of x1 plus the probability of x2. So this suddenly becomes all of a sudden, this expression right here, all of a sudden, if you imagine imagine uncertainty where the only outcomes are x1, x2 probabilities alpha and 1 minus alpha respectively. Then what's the expected value of x? Alpha x1 plus 1 minus alpha x2. So this would be your expectation of x. And that's your function out there. So what's this? With the probability alpha, you get the function of x1. With the probability 1 minus alpha, you get the function x2. So this will be the expectation of the functions. So you can see that for a concave function, it is true that the function of the expectation must be always within equal to the expectation of the function. For the love of God, please, 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 remember this. This comes in micro. This comes in risk averse, risk loving, risk neutral insurance, all those hedging contracts, future contracts, and so forth. How to avoid risk. One of the more fundamental results in micro. And by the opposite logic, and you really should draw a picture for each of these stories, right? This reverse statement will be true for convex functions. All right, we're moving pretty well here. Let's go back to variance. I already know what the variance says, right? This is the definition of a variance of a single variable. I now want to derive this shortcut. How do I do this? It's actually very simple. I'm not even going to do this for you. So literally, you have just opened out the brackets. And now you pass the expectation through. And now you have to be careful because, right, so this, of course, is nothing but the expectation of x. Right, so expectation of x times expectation of x minus 2 expectation of x squared plus expectation squared gives you minus expectation of x squared, right? And this, of course, you can see is nothing but the expectation of x squared. That's exactly what you see. And so you can see that the variance must be a number greater than or equal to 0. And the standard deviation is defined as square root of the speech right here. So how do I use this trick? So easy. Here's a joint PDF of x and y. We have already seen how to get just the density of x, and I've shown you already how to find out the expectation of x, and I've already shown you how to find out the variance of x the long way, which is this way, right? The long way. Can we use a shortcut? The shortcut says find out the expectation of x squared, and then subtract the square of the expectation of x. To find out the expectation of x squared, I simply have to do this, right? Which is x squared times the density of x. So I've done that for you. Here's x squared times the density of x. And then, of course, here is the expected value of x, which, of course, you already knew was 3/4 squared. So you find this number out. That's 0.6. 0.6 minus 0.75 squared gives you 0.0375. That's the exact same answer you got by the long method. So you're using this short cut. Covariances. Way back in as an undergrad, you vaguely remember covariances. If you're a U of T student, you remember Jen Murdoch screaming at you, rightfully so, that don't just because things look like they're moving together doesn't mean there's causality. These are associations. So the covariance of x and y is formally defined as this thing right here. Actually, before I show you this, maybe it's easy to see the stats version. Remember the stats version? Take each value of x, subtract with the mean, then multiply with each value of y, subtract with the mean, and then divide by n, sum it all up. So if x and y are together above the mean, then this would be a product. If x and y together are below the mean, this would again be a positive product. So you get something like this, right? So you vaguely remember that you can have a high covariance, which some people say is a strong positive association. I'm using these words loosely. You could have a negative covariance and seemingly have a strong negative association, etc., etc., etc. Right? You want to now show that this is the probability version of this. Here's your x, here's your x, here's your expectation of x, correspondence of the mean of y, here's your y, here's the expectation of y, corresponding to the sample mean of y, and now this expectation is the counterpart of summation divided by n. Right? You want to show that the covariance of x and y can be broken down into this simple formula. Expectation of x and y minus expectation of x times expectation of y. By the way, you already know how to get this, right? Remember this? Here's how we do it. Here's the definition. I open up the terms inside the brackets. You get this, right? Pass the expectation sign through. You should go home and see what happens. Simplify the expressions, and then you get this. Done. So the covariance of x and y is found by the expectation of x times y minus the expectation of x times the expectation of y. And as an exercise, especially MFEs, you should show that if x is a random variable, but y now happens to be a constant, the covariance between a random variable and a constant mathematically is going to be equal to a zero. And just as a side note, the covariance of x and y is up here. What about the covariance of x with itself? So wherever you see a y replaced with an x, and voila, you get the variance. So the variance of x is the covariance of x with itself. Example. So I want to find out the covariance of x and y. By the shortcut, I need to first find out the expectation of x times y. I actually did this earlier. I could have sworn we did this a few minutes ago. Right? And then I need to find out the expectation of x, which I also did earlier. I also need the expectation of y, which I also did earlier. Stick it in the formulas. Oops, shit, sorry. This is the expectation of y, my bad. Right? Stick in the formula. Done. The correlation. So let me ask you this question. So sometimes you hear people, especially amateur finance, people in finance, talking about the London Stock Exchange has a strong relationship with the New York Stock Exchange because they're a high covariance. You should never use covariance. Covariance intuitively seems to be picking up the notion of movement between x and y, right? The direction of movement, plus, minus, the strength of the movements, right? Does it look like a tight scatter plot or a loose scatter plot? But the problem with the covariance is you can't use it as a number to tell somebody that you have a strong or weak relationship because the values of the answer for covariance of x and y depends on the units of x and y. If you measure x and y in miles, you get one answer for covariance. If you measure x and y in kilometers, you get a different answer. So the covariance, the number covariance, is very susceptible to changes in units. That's why if you want to talk about the quote unquote strength of the relationship between two things, you're better off using something called the correlation. The correlation is defined as the covariance divided by the standard deviation of x and standard deviation of y. This is simple right here. In stats, it's success covariance divided by standard deviation of x, standard deviation of y, right? That's the analog over here. Notice that since standard deviation of x and y are always numbers bigger than or equal to 0, the sign of a correlation is always the same as the sign of the covariance. And this is a little bit advanced, but it's possible to show that the nice thing about correlations are they always are numbers between -1 and +1. So you can actually use them as a universal scale to tell somebody about the relationship, the strength relationship between X and Y, and explain why you can do this. I wouldn't lose much sleep over this. This is just telling you that, by the way, that you can also, express correlations this way. Yeah, boring. All right, a few more results before we do a few things. I showed you the expectation of a sum. What about the variance of a sum? It becomes a squared times the variance of x plus b squared times the variance of y plus 2ab times the covariance of x and y, which I've written down like this. You can prove this by using the following hints. I'll leave this as an exercise. It's not that hard to prove. And now we do an application. An investor wants to invest in a portfolio for the next 1 month, right? It's a 1 month portfolio, and she has two choices. She's going to stick X dollars of her own funds, so X dollars is her own money, for 1 month in a portfolio where a fraction 1 minus beta of the portfolio is a risk-free asset, and fraction beta is a risky asset. In reality, there is no such thing as a risk-free asset, right? So if somebody ever asks you what's a risk-free asset, it doesn't exist. But because a risk-free asset says it should be something whose returns are always guaranteed, in the sense that the distribution of future returns is a spike, a column. There is no variation. There's no histogram, so to speak of. Such things don't exist. But what comes pretty close to risk-free assets are quote-unquote government bonds, because unlike stocks, a paper that says I have an Apple stock, that piece of paper that says Apple stock makes no promises about the return or the price of that piece of paper tomorrow. But a piece of paper called a bond does make a promise that the holder of this piece of paper, the bond, upon maturity will get, let's say, some percentage returns. So certain assets are risk-free. For example, Canadian bonds issued, for example, let's say for short periods, as long as the investor holds on to that bond for the entire duration of that bond, and then cashes out in the same currency as issued. So if you're a Canadian bond holder, sorry, if you're a Canadian and you go buy a U.S. bond, and let's say you buy a 3-month U.S. Treasury bill. If you buy it, hang on to that bill for 3 months, you will get a guaranteed return in US dollars, which will be guaranteed as long as you don't bring it back to Canada. Because if you bring it back to Canada, then you face foreign risk, foreign exchange risk. So we have certain assets are risk-free. They're called, whose returns are certain. By definition, there's no risk going forward. A risky asset has expected risk RR, and future risk, as you know, is measured by standard deviation. If I have some more time, I'll explain why down the road. The answer, by the way, is not as simple as saying because of that stupid 65, or whatever, 68, 95, 99 rule. It's a little bit more clever than that. And here's the return of the portfolio and the risk of the portfolio. The return of the portfolio has a fraction 1 minus beta and risk-free, beta and risky. So by using the rules of expectations, you can show that this expression must be true. That the return of the portfolio is a weighted average of returns of risk-free and risky assets. What about the risk of the portfolio? The risk of the portfolio is something with the variance. The variance would then be 1 minus beta squared times the variance of the risk-free asset, which is 0. Then beta squared times the variance of the risky asset, plus 2 times beta times 1 minus beta, the covariance between a risk-free and a risky asset. But the risk-free returns are certain. They're a constant. That's why I asked you to do that exercise previously. And the covariance when a constant and something is random is 0. So it boils down to this. The variance of the portfolio is equal to beta squared. What fraction of your portfolio is sitting in the risky asset squared, multiplied by the variance of the risky asset. Well, when you take the risk of the portfolio, you get a very sexy formula, which is, of course, that is equal to the fraction of your money sitting in the risky asset multiplied by the risk of the risky asset. And by the way, MFEs, you should be able to take this expression. When will this return the portfolio be bigger than the return on the risky asset? And you just show that can only happen if you have a leveraged portfolio. It is physically impossible to beat a risky asset, let's say the market. You cannot beat the market on average in the long run unless you borrow money. So anyone who comes and says, yo, 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 what's up? I'll be the new Warren Buffett because I've been investing for 50,000 years and I've always been in the market is lying to their teeth because they didn't use their own money. They are either lying or they use somebody else's money. So you can only beat risky returns on average if you have a leveraged portfolio. Your money plus somebody else's money, not mine. All right. Why do we keep harping on this covariance correlation being a measure of relationships? Let's get it out once and for all. Supposing y and x have a positive linear relationship. In other words, y is equal to a constant times x. All I ask right now is beta is strictly positive. I'm not saying anything about the size of beta. Beta could be a small number, so there could be a weak relationship between y and x. Beta could be a large number, so there could be a strong relationship, but whatever. The variance of y, using the form that you saw previously, is equal to beta squared times the variance of x. The covariance of x and y, using the shortcut that we did earlier, you should go and do this, is equal to this thing right here. And when you find out the correlation, then you get a surprising result. It doesn't matter whether the scatter plot looks like this or whether the scatter plot looks like this, right? And it doesn't matter the slope is strongly close to 1 or close to 0. The correlation between two things which have linear relationship is always equal to 1. That's why in practice you use correlation as a way to measure, quote unquote, the relationship between x and y. The closer it is to 1, the stronger the evidence of a relationship between x and y. But what relationship? You can't use this word relationship loosely. Relationship, evidence of a linear relationship. So if you find a correlation of 0.999999, it's evidence that y and x have a strong linear relationship. That y has a is equal to a constant times x, where the constant is pretty. It could be any number bigger than 0, right? It could be anyway. Now comes the law of iterative expectations. This was the killer in grad school. It took a long time to understand what in God's name is doing this because, again, this is Harvard notation. Here's what it's saying. If somebody asks you to find the expectation of y from the joint PDF of x and y, okay, we can do it. But if you don't want to do this, you could do it this way. This says find out the expectation of y given x, which if you remember now is a function for the love of God, right, of x. And now take the expectation once again, but this time using the density of x. The two answers will be exactly the same. Here's a proof. What's the expectation of y? Using the joint density. If I use a joint density, I take y, multiply the joint PDF of x and y, integrate over x and y. But you already know that the joint density is the conditional density of y given x into the density of x. And now if I look at this term right here, where is this thing going? Sorry, let me. What I should have done was I should have actually brought this term. So I could have looked at this term right here. So here, take this term right here. Right? So I'll call this like this, dy, and now integrate. What that gives you, of course, is the expected value of y given x. Then you have your dx, and now since you're telling me to, and this is your fx over here, that's your fx over here. So what you're saying is, give me the expected value of y given x, but now carry out this expectation with respect to the density of x, and the answers will always be the same, right? So I'll leave this to Tommaso to show this to you. You can actually go to last year's test and see a numerical example. I probably should have done one. If I have time, I'll try to put one in. But let's do a practical interpretation. Oh, there it goes. Okay. So what you have here is let's say the Ministry of Finance has done a survey. They surveyed, excuse me, 10 groups of people. In group one, the average income level was, I'm just going to make this, and I don't know, what do you guys want to do? It's thousands of dollars. So it's actually 0.5, so let's see. So $500. Another group had average income 1,500, 2,500, etc. So there are 10 groups like this. Okay? So we have surveyed 10 groups. So and each of those 10 groups is random samples, so 10% chance of picking group one, group two, and so forth and so forth. And for each of these people with income 500 bucks, 1,500, so forth, I asked them the savings rate. The savings rate could be in the bins zero point 0.5, etc., all the way negative. Plus means you're saving, minus means you're borrowing. So this number means the following. Please be careful. This is the chance of y given x. So your x's are going this way, your y's are going this way. So this would be the probability of y equal to 0.25. See, y equal to 0.25, given that x is equal to 0.5. So what's the probability that you have savings rates of 25% given that your income is 500 bucks? And the answer is close to 4.9%. What's this? That's the probability of having a 5% savings rate given that you are somebody who earns 1,500 bucks. So there's a 24.7% probability that you save 5% of your income given that you have 1.5% of your $1,500 of income per month. All right. Notice that these columns are the conditional probabilities. These are frequencies, right? So these numbers adding up, going down columns add up to 1 because these are give the probability of y given that predicted value of x. What somebody wants to now do is, given this table, they want to find out the overall savings rate. So I know that people can fall into bins. Some people say 50%, 40 something, something, something. This particular person, in this particular category of people who earn 500 bucks a month, right? 4.9% or 5% of those people who earn 500 bucks will save 25%. Well, what about everyone? If I took every single person out there and what would the overall savings rate be? Ooh. Let's use the law of iterated expectations. Louis. According to Louis, I can do the following. I can calculate these expressions. And these expressions are the expected value of y given that particular value of x, which is 0.5. And here's how I get them. So I would find out, I would take each value of y times the conditional probability. So what I did was, let's go slowly. 0.5 times this conditional probability plus 0.4 times this conditional probability. And I do this times this, times this, times this, all the way to the end. When I add those things up, I get the expected savings rate was for people whose income category who earn 500 bucks a month. And you can see that those people, their savings rate on average is negative 1.16%. And surprise, surprise, as income levels go up, 1.5, 2,500, 3,500, you can see the conditional savings rates start to go up. See, they're going up, these numbers. Right? So now what you have are the values of E, expectations of Y, given X's. Right? That's what you have. But what you really want was the expected value of Y, right? Because that's the expected savings rate. To do this, we use Louis. Louis says, wait a second, for every income category, you know the expected savings rate, the expected the expected savings rate given that level of income. So sorry, I can't speak anymore. It's 1.5 hours nonstop, right? So these are all those numbers we just found out 2 seconds ago. These numbers down here, these at the bottom of the columns. Right? So for that income level, that's the E of yx. And since this income level was picked at, these are equally likely samples, 10%, 10%. I don't know why I did this twice. So this number is going to be observed in the sample with a probability of 10%. So if I now multiply so you can see in discrete form, what's this going to be? In discrete form, this is going to say the following: probabilities of x into the expected value of y given x. Maybe I'll fix this on the slides that I upload. This is exactly what you're doing. Probabilities multiplied with these conditional expectations is exactly what you see over here, right? Probabilities of conditional expectations. And when I sum them up, Louis says that when I do this, I should get the expected value of y, which is the overall savings rate. So in plain English, the entire sample, the average savings rate was just about 9.18%. Thank you.